Okay, seriously. Think about what these giant AI models can do today. They can write emails that sound just like you, answer questions you'd have to search for hours to find, even help programmers write code. It genuinely feels like magic sometimes, right? But where does that capability come from? And is it just about making these things ridiculously big, or does that sheer scale actually unlock something fundamentally new in how they understand and use language? That's exactly what we're diving into today. Our sources for this deep dive are centered around a landmark research paper from folks at Johns Hopkins University and OpenAI. They decided to push the limits and explore the power of massive scale and language models, specifically focusing on one you've almost definitely heard of, GPT-3.
Right. And this paper really zeroed in on a core challenge that's plagued traditional machine learning for years. Historically, if you wanted a model to perform a new task, say, translate from English to Swahili or classify sentiment in tweets, you needed a huge, laboriously assembled data set specifically for that task. You'd then take a pre-trained model and spend a lot of time in compute fine-tuning it, essentially tweaking its internal mechanics just for that one job. This work asked, can we bypass that painful fine-tuning step just by making the model incredibly, unbelievably big?
And our mission today is to walk you through this incredible paper.
Hmm.
We're going to unpack the approach they took, look at the often surprising results they got across a huge variety of language tasks, and then dig into the really important implications and limitations that come with models this large. So let's jump straight into the source material they put together for us.
Absolutely. And the core concept they explored, the big idea here, is something called in-context learning or few-shot learning. Forget about needing a massive labeled data set to permanently change the model's parameters. Think of parameters like the millions or billions of adjustable knobs inside the model that it tunes during training to learn patterns. Instead of changing those knobs for every new task, they tested if a giant model could learn to do a task just by seeing a few examples or instructions right at the moment you ask it to perform. It's kind of like showing a human how to do something complex with one or two quick demonstrations right before you ask them to do it, rather than sending them away for weeks of specialized training.
Okay, I get it. So the paper describes this using different levels of shots, right? Based on how much context you give the model and the input.
Exactly. They broke it down into three main settings. First, there's zero shot. Here, you give the model only a natural language description of the task. For example, you'd just write, translate English to French. This is the hardest test because you're giving it no examples whatsoever, just hoping its pre-training taught it enough to understand the instruction. Sometimes that's tough, even for humans without an example.
Right, like figuring out a really specific formatting request just from the description.
Precisely. Then you have one shot. This is where you provide the task description plus just one example of the task being done. So, translate English to French, cheese equals fromage. This is probably the closest analogy to how you might quickly show a human how to do something new with a single demo.
Okay, just one hint.
And finally, few shot. You provide the description and a few examples, typically between 10 and 100 examples, because that's roughly how many would fit within the input limit or context window of their model, which was 2048 tokens. Tokens are basically pieces of words or punctuation. The whole goal of few shot is to see if the model can pick up the pattern and perform the task correctly from these examples without you needing to go back and change its internal parameters through fine-tuning.
And you're contrasting that sharply with fine-tuning, which is the traditional heavyweight champ, right?
All right.
Where you do update the model's internal parameters using a big task-specific data set.
Exactly. And the source highlights the big downsides of fine-tuning. You need those large, high-quality labeled data sets for every single new task. That's a huge bottleneck. And there's a risk that by focusing so heavily on one task, the model might learn an overly narrow distribution, essentially getting too good at just one thing in one very specific way.
So it might not generalize well.
Right. It might not handle slight variations in the real world. Few-shot learning, if it works, bypasses both of those issues.
Got it. And the model they focused on for this was GPT-3, and the scale is just, well, mind-boggling.
It truly is. They actually trained and studied 8 different sizes of models, starting from a relatively small 125 million parameters, all the way up to the headline model at 175 billion parameters.
175 billion.
That's the one people typically call GPT-3. For context, the previous large model, BERT large, was around, 340 million parameters? So 175 billion is a colossal leap.
Wow. Okay.
And this giant was trained on an equally colossal data set, 300 billion tokens of text, primarily scraped from the internet, with a huge chunk from something called Common Crawl, which is essentially a massive public archive of web data.
Wow. 300 billion tokens, that's like reading the entire internet several times over, almost.
Pretty much. And what's fascinating is that they found the model's core performance measured by something called validation loss, which is basically how well the model predicts the next word it sees. Lower loss is better follows a smooth power law trend as the model size increases.
And that power law trend is a huge deal, right? It suggests scaling just keeps working.
It really is. It suggests that, unlike a lot of technology or even biological systems where you quickly hit diminishing returns, simply making these language models bigger seems to keep yielding predictable, fundamental improvements in their underlying language modeling ability. It suggests that, at this scale, we might not have found the ceiling yet just by turning up the size knob. And this trend held consistently across models ranging over 3 orders of magnitude in size.
Okay, so they built this giant model, trained it on a mountain of internet data, and then tried this in-context learning thing. The big question is, did it actually work when they put it to the test?
And based on the paper's results, the answer is a pretty resounding yes in many cases. They tested GPT-3 on a vast spectrum of language tasks. Generally, they observed that few-shot performance consistently improves with both the overall size of the model and with the number of examples you give it in the context.
More examples help more. Makes sense.
Right. And the really interesting part, the larger models showed much better gains from seeing those in-context examples than the smaller ones did, which strongly suggests that scale is somehow enabling or enhancing this ability to learn from just a few examples. It's not just memory, it's learning on the fly.
Let's hit some of the specific results that jumped out from the source material. What about question answering? That seems like a core task.
Yeah, this was a strong area for GPT-3. In a closed book setting, meaning the model can only use the information it learned during its initial training, it can't go search the web or look up facts.
So it's in its head, basically.
Exactly. GPT-3 achieved seriously impressive results. Its few-shot performance on a benchmark Cointrivia QA hit 71.2% accuracy. Now, what's key is that this result is actually state-of-the-art compared to other models that were fine-tuned specifically for closed book QA.
Wait, so few shot, with just examples, beat models specifically trained for the task.
In that setting, yes. It matched or approached the best fine-tuned models on several QA datasets, all without any task-specific fine-tuning. That's a big deal. It shows the power of scale and the pre-training.
Okay, that's surprising for factual recall.
Yeah.
What about something like math or reasoning, usually seen as harder for these models?
Surprisingly, the model demonstrated capabilities here too, again in the few-shot setting. It showed an ability to perform simple arithmetic, like 3-digit subtraction or 4-digit addition.
Really, addition and subtraction.
Yeah, and also unscramble words like anagrams and even tackle SAT-style analogies. And the paper's analysis on the arithmetic tasks was particularly insightful. They checked the overlap between the test problems and the training data and found it was very low, less than 1% for 3-digit addition.
So it wasn't just memorizing answers it saw online.
Seems unlikely. Instead, it appears to be attempting the computation. They even observed it making mistakes that look like computational errors, like forgetting to carry a 1 in addition.
Huh? Like a human kid learning math.
Kind of. It hints at a more fundamental capability emerging beyond just pattern matching or memorization.
That is fascinating. It's not just recalling, it's trying to do the thing. Okay, let's pivot to something more creative, like generating text. The source talks about news article generation, right?
Yes, and this section has some of the most striking findings, I think, for a general listener. They gave the model titles and subtitles and asked it to generate short news articles, typically between 200 and 500 words.
Standard sort of task.
Right. Then they ran experiments where humans were given articles and had to decide if they were written by GPT-3 or a human. Now, for a control model, which was contentionally less capable, humans are pretty good at spotting the AI text, around 86% accuracy.
Okay, understandable. You can usually tell if it's a bit clunky.
But for the full 175 billion parameter GPT-3, human accuracy plummeted to barely better than chance, around 52%.
52%, that's like flipping a coin. That is wild.
It really is. And this was true even for longer articles, and when the human participants spent more time scrutinizing them. The paper's finding here is quite clear. Human ability to detect model-generated text seems to decrease significantly as the model size and quality increase.
Wow. That has some serious implications we should circle back to.
Definitely.
Any other performance highlights from the source before we move on?
Yeah, a couple more. They also showed near state-of-the-art results on some tricky reading comprehension tasks like CoQA and record. And they found that GPT-3 using few-shot prompting could outperform a fine-tuned BERT-large model on many tasks within the SuperGLU benchmark, which is a collection of challenging language understanding tests.
So beating fine-tuned models again, but on harder tasks.
Often, yes, and usually with far fewer examples in the prompt than BERT-large used for its entire fine-tuning dataset. It even showed some surprising ability in translation, despite being primarily trained on English data.
Okay, so it sounds like few-shot learning with a giant model is a slam dunk everywhere then. Solved.
Not quite. And the paper is quite balanced here, which is good. They highlight areas where few-shot wasn't a magic bullet. They found GPT-3 showed notable weaknesses on tasks that require comparing two sentences or snippets of text.
Like figuring out nuances between sentences.
Exactly. Tasks like determining if a word is used in the same way in two different sentences, a benchmark called YC. Its few-shot performance there was essentially random chance.
Right.
It also struggled on natural language inference tasks like ANLI and RTE, which involve figuring out if one sentence implies another or contradicts it.
Interesting that it can do, say, arithmetic, but struggles with that kind of sentence comparison. Seems counterintuitive almost.
It does highlight that these models don't have a uniform, human-like understanding across all types of language tasks. Their capabilities are still quite specific, even if broad. And speaking of things it doesn't do well, the paper is quite direct about GPT-3's general limitations, even in generation. While samples can be high quality, they found they can still sometimes repeat themselves semantically, lose coherence over very long passages.
Right, the repetition problem.
Contradict earlier statements or include sentences that simply don't make sense in context, non sequiturs.
So the long-form coherence isn't totally solved yet, even at that scale.
Not based on this paper's findings at that time, no. They also specifically called out weaknesses like difficulty with certain common sense physics questions. Simple things like knowing whether cheese melts when you put it in a fridge.
Which it doesn't, usually.
Right. And as we mentioned, those sentence comparison tasks like YC and ANLI remained weak points for the few-shot approach.
Okay, so powerful but flawed.
Definitely. And another really important point the paper addresses head-on is data contamination. This is a major methodological concern when you train a model on practically the entire internet.
Oh, right. The risk is that parts of the test sets for the benchmarks you use might accidentally have been included in that massive training data because, well, they exist somewhere online.
Exactly that. And if the model saw the test questions or answers during training, its performance isn't a true measure of its ability to generalize. It might just be memorizing.
So it looks smarter than it is on those specific tests.
Potentially, yeah. The authors explain they did attempt to filter out known test and development sets from their training data, but they mentioned there was a bug in their filtering process, so some overlap unfortunately remained. And retraining a model of GPT-3's size just wasn't feasible to fix it post hoc.
Okay, so they knew there was some risk. How did they handle that in the paper? Did they just ignore it?
No, not at all. They systematically checked for this remaining overlap using methods like n-gram analysis, which looks for sequences of words present in both the test data and the training data. Their check was intentionally conservative, meaning it probably flagged more potential overlap than actually existed, but they wanted to be careful.
Better safe than sorry.
Right. They then analyzed the impact of this potential overlap. For most benchmarks, they found that while there might have been some training data overlap, it seemed to have a minimal effect on the model's reported performance. However, they did flag some specific cases like the PIQA and Winograd benchmarks where there was detectable overlap, and the model's performance did decrease slightly on a cleaned subset of the data where they tried to remove contaminated examples.
Okay, so it mattered sometimes.
It did. And for reading comprehension tasks like SQUAD and JIROP, they found that while the source text, like a Wikipedia article, might be in the training data.
Which is hard to avoid.
Exactly. But the specific question-answer pairs used for the benchmark were generally not found in the training data. So the model couldn't just memorize the answers, it still had to find them in the text. And they were transparent that certain language modeling benchmarks were so heavily contaminated, they weren't reported at all in the paper.
So they took it seriously and tried to quantify it. But it's a known factor, kind of asterisk, on results from models trained this way.
Precisely. It's a challenge inherent in training on such massive, unfiltered data sets. You just scoop up everything.
All right, shifting gears a bit. So what does this incredible capability, combined with the limitations and these challenges like contamination, actually mean for you, for me, for the world? Models like GPT-3 clearly have Huge potential benefits, revolutionizing how we autocomplete code or emails, improving search, generating creative content like game narratives, assistive technologies. The list goes on.
Absolutely. But the paper is quite deliberate in also focusing on potential downsides and risks. They explicitly state they're doing this to encourage study and the development of mitigation strategies. One major point they highlight is that the vastly improved quality of the generated text, as we saw with that news article example, well, it makes it significantly harder for humans to distinguish between synthetic text and human text.
Yeah, that 52% accuracy number is sticking with me. That's a pretty concerning milestone when you think about it.
It is. Because the source discusses how this lowered barrier to generating high-quality text could be used for deliberate misuse. Think about things like generating highly convincing misinformation campaigns at scale, writing much more effective spam or phishing emails that look legitimate.
Or generating fake reviews or fraudulent academic essays.
Exactly, or developing content for social engineering attacks. The sheer quality means these could be much harder to detect and potentially more effective than previous attempts.
So it lowers the bar for bad actors.
Potentially, yes. The paper analyzes potential threat actors who might use this technology and notes that at the time of writing, even sophisticated groups hadn't widely adopted these models yet. They hypothesize this is partly because the models weren't reliable or controllable enough. They're often stochastic or somewhat random. Nature means you still needed significant human oversight and review.
So you couldn't just automate everything.
Right, which limits how much you can scale up malicious operations. But the authors raise the concern that if future models become more consistent and steerable, that calculation changes. That could pose significant challenges to society.
That's a chilling thought, that the main thing holding back widespread misuse might just be that the models aren't quite reliable enough yet. It sounds like a ticking clock.
It's certainly a significant concern highlighted by the research, yeah. It underscores the urgency for ongoing study and development of safety measures alongside capability improvements.
Definitely.
The paper also goes into another crucial impact area, bias. This is a huge topic with these large models.
Right, because they learn from the internet, and the internet is, well, full of biases.
Exactly. They point out that models trained on vast amounts of unfiltered internet data are inherently going to reflect the biases that exist within that data, which means they reflect socio-historical biases present in society.
And did they find specific examples in GPT-3?
They did. They detailed some specific findings from their own analysis. Looking at associations with gender in their tests using neutral prompts like the occupation was A, they found occupations were heavily associated with male identifiers. 83% of occupations leaned male in their test setup.
Wow, 83%.
And this bias often increased when they used prompts like the competent occupation was A. They found occupations requiring higher education or physical labor tended to lean male, while others like midwife or receptionist leaned female. Separate tests looking at co-occurrences showed female pronouns were much more associated with appearance-related words like beautiful, gorgeous, compared to a broader range of descriptive words associated with male pronouns.
Oh, okay. What about race?
In tests regarding race, using prompts about racial groups, a sentiment analysis showed words associated with Asian had consistently high positive sentiment, while words associated with Black had consistently low sentiment across the various model sizes they tested in that specific setup.
Consistently low for Black. That's concerning.
Very. And for religion, specific words co-occurred more often with religious terms, while expected terms like Ramadan and Prophet co-occurred with Islam, concerningly. Terms like violent, terrorism, and terrorist were also among the top 40 most favored words in their test setup associated with Islam.
Oh, wow. That's problematic.
Extremely. They explicitly state that these associations reflect the socio-historical factors present in the training data and that more sophisticated analysis is definitely needed. But their findings clearly demonstrate that the models do reflect these biases learned from the internet. They soak it all up, the good and the bad.
It's such a stark reminder that the training data isn't neutral, and so neither are the models trained on it. They're like a distorted mirror of the text they learned from.
Exactly. And finally, the paper also briefly mentions the significant energy usage required for training and running models of this scale as another important impact area to consider. It takes a lot of power.
Right. The environmental cost. Okay, wow. So this deep dive into the GPT-3 paper really shows us a model built on an unprecedented scale. It demonstrated surprising, almost emergent, new capabilities like this in-context learning, achieved strong performance on many diverse tasks without needing task-specific fine-tuning, and generated text so convincing it could fool most human evaluators.
But, as the paper clearly lays out, it also has real limitations in areas like long-range coherence or certain types of reasoning. It's susceptible to issues like data contamination from its training set. And maybe most importantly, it starkly reflects the undesirable biases present in the massive, unfiltered internet data it learned from. The research highlights that simply scaling up models trained this way is a powerful tool, yes, but it's absolutely a double-edged sword. It unlocks incredible capability but also amplifies significant risks.
It really makes you think about the future, doesn't it? As these models inevitably continue to improve in reliability and controllability, addressing some of those current limitations we talked about. How do we ensure that we maximize the tremendous potential benefits, the coding help, the writing assistance, the creative generation, while also effectively grappling with the very real potential for harm? And how do we ensure that they reflect the best, most accurate, and least biased aspects of human knowledge and language, rather than just replicating the noise, the misinformation, and the biases that are also found online? We'll leave you with that thought to mull over based on everything we've discussed from this fascinating source material.